Hi, everybody, and welcome back. Our next topic of discussion is actually going to be a huge shift to a new application for calculus. So up until this point, our main focus has been on differentiation and how we can use a derivative as a function of change for the original function. But today we're going to learn the first application for integration. So the first section, our last video, focused on the reversal of the differentiation process and how we can work backwards to figure out what the original function was if we start with a derivative function. Eventually, we are going to link those two things together. Integration and differentiation, we're going to learn in a couple sections how those two things relate to one another and how the world of calculus kind of becomes this ever-looping cycle between derivatives and integrals. But first, we need to kind of build up to that, and that's what we're going to take a look at today with being able to find an estimation for the area under a curve. So to the right here on your notes page, we have the graph of the function f of x equals negative x squared plus 2x plus 3. And we've shaded in that portion of the graph on the interval from 0 to 3. So we've shaded in the area between the x-axis and this function. So we're commonly going to refer to this as finding the area under a curve, but really what it is we're finding the area between a curve and the positive x-axis, or excuse me, in this case it's the positive x-axis because of the interval, but it'll just be between the x-axis and some function's curve. And so that's why we've shaded that particular region in. Now, even though it looks like the y-axis is a boundary, it's not always going to be a boundary. That is because we're starting at x equals 0. So if x equals 0, that really is the y-axis. So eventually, what we're going to build up to is learning how to find the exact value for this area. But we're going to have to start off with some baby steps. So that's our ultimate goal. We want to find the area of this region. So right now, that task is impossible without calculus. There's no way for us to find the area of that region, the exact area of that region, without using calculus. But what we can do is come up with some pretty good estimates. So if you guys thought about this and we really had to come up with a decent estimate, there's all kinds of different strategies that we could use to come up with an estimate. Just right off the bat, trying to come up with a quick estimate, well, we definitely have at least an area of 6 units squared because there are 6 unit blocks contained within that shaded region. So that part's easy. But then we have all these little partial blocks, and we have to kind of estimate what those all total up to. So one strategy, and it's the strategy our focus is built on, is using known geometric area formulas. So shapes that you guys already know how to find the area for, and applying that to the region. For example, this little part of the curve within this unit cube, or unit block, excuse me, is kind of triangular in shape. Now, it's not exactly triangular in shape. Let me zoom in here to this graph a little bit. So it's not perfectly triangular, but if I were to draw a triangle, let me get a line here. That's not that far off, okay? So that triangle, if I draw all 3 edges to it, that triangle accounts for half of that unit block, so that it has an area of 0.5. So if that's 0.5, you can see the actual shaded region is just slightly more than that. But again, our job right now is just to estimate this area. We know the actual value is impossible without a lot of calculus. But that also means I could do the same thing with all these partial ones. So I could estimate that guy. Now that's a little bit more shaded region left over, but 0.5 is still a decent estimate. And then for these guys, these are a little bit more difficult. I wouldn't really be able to estimate the dimensions of that triangle, but what I could do is draw one big triangle. Since this part of the curve is exactly at that tick mark, I could just make this one big triangle. So that would have dimensions of 1 by 3, so its area would be 1/2 base times height, or 1.5. So what I could say here is that the actual area of that shaded region is approximately equal to the 6 unit blocks that are totally contained within that region, plus the 2 halves, and then plus the 1.5 from that big triangle. So we get an approximation of 8.5 units squared. So now once we have an estimate for this, then we want to explore how can I make this better. So that's really the process of all mathematics. We set a goal, we come up with ways to estimate, to predict what's going to happen, and then once we start to see underlying patterns, then we go back and try to refine the process to make it as efficient and accurate as possible, and oftentimes that will lead us to methods that can help us calculate or evaluate the exact answer. And that's really all that calculus is about. Same idea with derivatives. When Newton and Leibniz were discovering their different methods for finding that instantaneous rate of change or the slope of that tangent line, again, remember, it all started by calculating the slope between 2 points and looking at patterns or ways to refine that and scoot the 2 points closer together, and using limits, they achieved that goal. But we're really going to kind of approach this with that same mindset. We're going to start with a very finite, simple, straightforward process, and then we're going to look and see how could I possibly make this more accurate. Well, for this, all I really did was just look at basic shapes that kind of look like they exist within this shaded region. There was no structure. If I gave you a different function and it had a different shape to it, then my approach using this kind of mindset would have to be probably completely different, because I would have different shapes contained within inside of that. So we can use our pre-existing knowledge of geometry and a little bit of problem solving to make this happen, but we don't want to have to start from scratch every single time we start with a new function or a new curve. So instead, we're going to look and see how can I make this a repeatable but accurate process. So that's our ultimate goal here. So the method, or the way that we do this, is through something called Riemann Sums. So again, without calculus, our best option is to estimate these kinds of regions using basic geometry. This process is called a Riemann sum, named after the guy who figured all this out. So a Riemann sum is the result of finding the total area of numerous geometric shapes used to approximate the area under that curve. So again, this was a very basic example of that, but for this case, I use squares and triangles. Now, using different shapes all combined together is one way to do it, but it's not the most efficient way to do it. So there's many different ways, but they all revolve around breaking up the region into smaller pieces. So we first will break the large interval into smaller pieces called subintervals. So the first example there, we said that we were looking at the region created by the curve on the interval from 0 to 3. So to make this an efficient process and to make it as accurate as possible, what we're going to do is we're going to take that interval and break it up into subintervals, so smaller chunks. And then we're going to look and see what kind of shapes can be made within each of those subintervals. So for example, for this guy, an easy way to break up the subintervals would have been by a unit of 1. So we could have gone from 0 to 1, 1 to 2, and then 2 to 3, and then look and see what shapes can I see or create within each of those subintervals. We can always pick different values of x. They don't even actually have to be the exact same width. Again, to make it efficient and as simple for us to repeat as possible, then having those equal subintervals is very helpful, okay? Now, throughout this section, we're going to look and see different ways of breaking it up, and we're even going to use different shapes. But if we think back to the most basic shape, the easiest area formula that we have ever worked with throughout all the math you've learned, it would be the area of a rectangle or even a parallelogram is just base times height. So because this is the easiest area formula, a rectangle is going to be the easiest shape for us to use to calculate the area of these regions. Now, you might be asking yourself, well, if I go back here and I draw a rectangle from 0 to 1, and I go up to this curve, if I draw it on this side and use the right side to dictate the height, then I have all this little extra area that I'm including. Same thing on, or excuse me, not the same thing on this side. Let me get rid of these triangles here real quick. If I go to use the right edge for the next interval from 1 to 2, well, now that rectangle is super short. Now there's all this area that's unaccounted for. But these two kind of balance each other out. Now, when I go to do the next one, if I used my right endpoint for the third subinterval, then that's going to be way off because the right side from 2 to 3 would actually be down here. So that rectangle would have a height of 0. So all of this area is unaccounted for. So sometimes we could use the right side of these subintervals. Other times we may choose to use the left side. If I was to use the left side to draw these rectangles, then if I went from 0 to 1, 0 would be the left edge. So I would go up until I hit the curve, and now that's the height of that rectangle. Again, we see unused space, so we're a little short. But now if I use the left edge on the next one, that would spit me out over top. And again, you can kind of see they balance each other out. Not exactly, but fairly close. But now this last one, left edge, now we're going to have a ton of extra unused space. So there's a give and take a little bit with this process. Depending on which part of the subintervals we use, sometimes we're going to be a little bit under, sometimes we're going to be a little bit above. But again, we have methods, and you're going to see we are going to refine this process to make it as accurate as possible. So when we do these, there are basically 4 common methods for breaking these intervals up and trying to make these approximations. So the first one, the first 2 I just showed you guys, is either a left endpoint Riemann sum or the right endpoint Riemann sum. So basically what that means is we pick either the left edge or the right edge to use as the height of the rectangle, and then we calculate the area for that rectangle using the width and the height. Another option, a better option, but it's a little bit more work involved, is using the midpoint. So you guys saw here with this basic example, each one of these has kind of its issues. The left endpoint, you see we have a lot of extra white space, so that's going to be probably an overestimate. The right endpoint, though, you saw that for the last subinterval, it was way down at the bottom, so we had all this unused space. So that one would be a severe underestimate. Well, a midpoint is we just go right in the middle of the subinterval. So instead of picking left or right, we would use the exact middle of the interval. So if it's from 0 to 1, then at 0.5, I would go up until I hit the curve, and that's what I use as my height. In doing so, a lot of times what we see happens is it's a much closer approximation for the real area for that piece because it kind of splits the difference. So part of this is extra, part of it is missing, but these two tend to balance each other out a lot better. Same thing here at 1.5, so this would be just slightly higher than that first rectangle. Okay, now again, it's not going to be perfect, but you see a little bit unused, more is extra in that one. But then for something like this last one, this is definitely a benefit because now we don't either, instead of having no area or way too much, this is going to be kind of right in the middle. So again, it's not perfect. We're still missing some and we still have some extra, but these do a much better job of trying to balance each other out. Okay, so that's the midpoint Riemann sum. And then the last one, it's definitely the most difficult to do, but it's also going to be the most accurate. So, and that one is called the trapezoidal rule. I don't want to explain that one or get into it too much right now because it's going to be a focal point towards the end of this section. So we'll kind of save that one, but you guys can start to brainstorm what that might look like or how that might work if we tried to use trapezoids instead of rectangles, or why there would be a benefit to doing so. So just keep that in the back of your mind as we go through this. So when we carry out this process, we would like 2 things to be true. Again, we want the process to be repeatable and efficient, even for different sets of conditions. So different curves, different intervals, different subintervals, whatever we can throw at you, we want it to be repeatable and efficient. That's our number 1 goal. And then 2, we want the estimations to be as accurate as possible. So the worst thing that I could do here is just draw one big rectangle around the whole thing. yeah, we contained the whole thing. It was super easy and efficient, but it wasn't accurate. So oftentimes what you'll see is for a estimation to be really super accurate takes a lot of work. But if we refine the process and make it easily repeatable and efficient, then we can kind of get both of those things to be true. So that is our goal here. So we're going to kind of go through the nuts and bolts and explain this process and do all the setup before we'll actually dive in and try some. So bear with me. So whenever we approximate the area, our first step, the very beginning of this process, it's always going to start off with us needing to know how wide our interval is, so the whole thing from start to finish. So we refer to that interval as A to B. So you always be given the two x values, so A is our first, B is our last. So that's the span of the x-axis or part of the curve that we want to cover. And then we also need to know how many chunks we want to break it up into, because that will determine the overall width of the whole thing. Or excuse me, the width of each individual piece. So we're going to take the whole thing divided by a certain number of pieces, and that will determine our width of each subintervals. So again, I mentioned earlier, sometimes we will have different subinterval widths. It's not a requirement that they're all the same, but it definitely helps us speed up calculations, and it's easiest and most efficient for them to be the same width. So if we have equal subintervals, then to determine that, we will take the width of the entire interval, b minus a, and then we just divide it by the number of rectangles or subintervals. Again, most of the time we're going to be working with rectangles, but for that trapezoidal rule, we're going to switch shapes. But n is still going to represent that. No matter what, how we go about our estimations, n will represent the number of subintervals that we have for the problem. So we represent the width of each subinterval with this special notation, and we read that as delta x. Again, delta is kind of a way of representing change. So this is like the change in x for each piece. So another way of thinking about it is on my x-axis, if I start at A to get to the next subinterval's x value, we are adding a delta x to that. So that would kind of be like the next A value. And then we'll do that again, add another delta x. That'll take us to the next one. And we will continue that process until the very end, we should end up at B. That's the idea of these equal subintervals. But calculating this value is the very first step in this whole big process. So we have to know how wide each of our rectangles are. So if you think about it, by calculating this, we actually have one dimension of every rectangle that we're going to end up with. That's why it's so efficient to have the same width. That way it's common and we can speed up the calculations. So to find the area of a rectangle, remember we just have to know width and height. We now know how to calculate the width of each one, so we just have to come up with a way to calculate the height for each rectangle. So we're able to dictate or change the width of each rectangle, but their individual heights will always depend on the height of the curve at each of those different x values. So we have a system to determine values or which values are going to be used as our endpoints for the rectangles, but we have to actually depend on the curve or the function's equation to determine the heights. So at each of those x values, to calculate that value or the height of the rectangle, we're actually going to have to evaluate the function at each different value of x. So for each one, to calculate its width, we are going to use delta x, that's the b minus a over n value, and then multiply it by its corresponding height for each different rectangle. And again, that is calculated by taking f of x sub I, or whichever value of x we are working in. So for example, if I wanted to calculate the height of my third rectangle, then that would correspond to f of x sub 3. That's the idea. That's the notation and how we go about this. So once I put all of that together, I have a pretty efficient, repeatable way to calculate the area for all of these rectangles. So for the first rectangle, I would take its width, b minus a over n, multiplied by the first height. So the value of the function at x sub 1. Then for the second rectangle, I take the width, which is the same thing, b minus a, times the second value of the function, or the second height. So if you notice, we're just going to repeat this process until we get to the very last one. But all of these have the same width, a part of that. So just to speed this process up, because they all have the same width, we're actually able to factor that out of this whole big expression, and we can write it in a much more efficient way. B minus A over N, again, that's our delta X, times the sum of all the different heights. F of X sub 1, F of X sub 2, all the way to the last one. These are all just heights, okay? So that's all this is inside of here. We're just going to total up all of the heights, the different heights that we use along the function's curve. That is as quick and easy and simplistic but repeatable as we can make it. So that's the easy part. Now we have a system in place. Now we want to be as quick as possible with coming up with all of these parts. But we have the overall end structure in place that we have to kind of build up to. So to be able to do that, we need to be able to identify subintervals and endpoints. So that's our next job. So again, we have options. Again, there are different methods for creating those rectangles based on which value of X that we choose. So with all of these, though, we begin by identifying the subintervals. So to create these, step-by-step process. First, we need to know the width. And then again, just like I showed you on the number line before, we're always just going to start at our A value because that's where the interval begins, and then we're just going to keep adding delta X over and over and over again until we reach our end value for the whole big interval. So from A to B, that's all we're doing. We're basically just taking that whole thing and chunking it up into pieces. That will provide us with a list of all possible values of X that could be used as endpoints. A couple different ways to represent it. Some people like the X sub 0 instead of A, and then X sub 1, X sub 2, so on and so on until we get to X sub N, that is really B. Some people like A and B. It really doesn't matter. Basically, this is just a list of all the possible values of X that could ever be used as endpoints. Another way is based on the math that we use. So the first endpoint is just our A value. The next guy is A plus 1 delta X. Then A plus 2 delta X's, and then 3 delta X's, and so on until we get down to that very last guy. So again, just different ways to represent the endpoints, the possible values that I can use as endpoints. But then to actually create the subintervals, again, each subinterval goes from one endpoint to the next guy on this list, and then that one to the next one, and so on. So seeing it written in this list may not be the easiest way for you guys to wrap your head around it. So again, another way of thinking about it is on our number line. So if I start at A, then the next one would be A plus 1 delta X, and then A plus 2 delta X's, and then A plus 3 delta X's. I didn't space these out enough. But if those are all the list, or the list of all the values on there, then again, each one of these sets is just one endpoint to the next. So that is my first subinterval. So I can make my first rectangle using those guys. And then the next one spans from the second to the third, and then third to the fourth, and fourth to the fifth, and so on. That is how we create these subintervals. So from that list then, now we have to identify which ones we're actually going to use to make the rectangles. And again, we want to be consistent. We don't want to use a left endpoint for one interval and then a right endpoint for the next one and then constantly bounce back and forth. Because if we do that, then we can't repeat, or we can't use our quick, efficient, repeatable process here. We have to stay consistent. So we're going to use all the left endpoints or all the right endpoints. So basically, if I were to do that and use all of the left endpoints, then the first, or the set of endpoints would be the very first one. So that would be A, and then A plus delta X, and then A plus 2 delta X. So basically, all of the numbers on this list except for B, because B would be the only value on that list, on that number line, that couldn't be the left edge of a rectangle. Everything else would be the left edge of a rectangle except for the very last guy on that list. So if you notice, the heights created using those, it's f of each one of those, except for there is no f of b on here. If I were to use right endpoints, then it's the exact opposite. We would use everything on the list except for A, because now A can't be on the right side of an subinterval or a rectangle because it's on the left side. It's the very first one. So for this list, another way of writing this very last guy, that is really just f of b. So once we have the endpoints that we're going to use, that will allow us to come up with the heights that we're going to use, and then we can just do all the math. So the math is actually the easiest part of this whole process. It's really setting everything up and gathering all the information that we need that can be a little time consuming. So the way that we can get those values or get the information will kind of dictate how time consuming or difficult the whole thing is. So there are a handful of different ways that I could deliver the information to you that we need. But no matter how I give it to you, the system, the structure, and the process are really always going to be the same thing. I'm going to find my width of my interval, find the width of my subintervals, which again is a part of that is how many of them I have. Then I can make a list of endpoints. Then I pick out which ones I need. Then I use those to get my heights. But once I have that list of endpoints, how we get our heights really does depend on how I give you information about the function. So one option is I give you a graph. So if you have to find your heights given a graph, well, once we have our list of endpoints, we just have to go to the graph and figure out at x equals 2.5, what's the height. So that one, it's really just about looking at the graph and figuring out what the y values are. Sometimes I will give you a table of selected values. So the table in that case will tell you what x values we can actually choose from to use as our endpoints and their corresponding y values. So this would be the trickiest of all of these because a lot of times our table is not always going to have consistent widths between those values of x. And worst case, if we don't have the equal width, then we just have to use what we're given. And sometimes that's as best as we can do, and that's okay. Okay. Now, the third option is definitely the most difficult because it involves the most work, but it often reveals the most accurate results because we're not hamstrung by the information that's given to us. So if I give you the function, then we will be giving you a specific interval, a function equation, and the number of subintervals, but then we can go about calculating our own delta x, and we can come up with our own x values, and then we can come up with our heights. So it's not as much guesswork when I actually give you the function, but the drawback there is it's a little bit more work. So again, though, no matter what, no matter how I give you the information about the function and how we go about coming up with the heights, the end result's going to be the same thing. Our goal is to be able to use this equation to make a repeatable and accurate process for estimating the area under that curve. So again, so this is if we have equal subintervals. That's the ideal scenario. But if worst case, we are not able to do that, and again, that's going to happen most often with either a graph or a table, we may be forced into using unequal widths. If that's the case, then it's not that big of a deal. We just have to find width and height for each different subinterval or each different rectangle, which at the end of the day, it's just multiplying and adding. So no matter what, the math really is the easiest part of all this. All right, so enough talking about it. Let's actually try and do one. So for this one, I've decided to give you a graph. And again, the information can be presented in a handful of different ways. But I've got the graph of some function, kind of looks like a quadratic, but it really doesn't matter what equation it is. And we're looking at the area under the curve on the interval from 0 to 2. So right off the bat, I can acknowledge that is my A and B for my interval. And then we're going to do this process using 4 equal subintervals. So that means 4 is my n value. So we're going to do left endpoint Riemann sum and then a right endpoint Riemann sum. So for both of these, though, I'm going to do this kind of off to the side because the information will be the same for both. Again, our delta x is equal to b minus a divided by n. So in this case, 2 minus 0 divided by 4, or 1/2. So that is the width of each subinterval. So it's actually the size of each tick mark here. So on the graph, I'm just going to go ahead and plot the values of x, or the points where we have these endpoints. All right, so now we're going to take our values of x, we're going to come up with a list of our endpoints. So again, this is a list of all possible endpoints. Then when we actually get into each problem, we'll come up with the actual list of the numbers we're going to use. So I'm going to label this guy as the set of all x sub I. So again, which one it is really depends on which endpoint, which rectangle we're looking at. But when I want to make a list, I just use these squiggly brackets to show that it's a set or a list of values. So again, one way to build this is to start with A, so that would be 0, and then we just add our delta x over and over and over again. So that would be 1/2, 1, 3/2, and then our very last one, if we keep going, we're just going to stop once we get to our B value. So if you didn't have a graph and you couldn't see these numbers, then that's the process that we would go through. Start with A, add that delta x value over and over again until we get to B. But with a graph, it's just as simple to look at where we've placed those points. So that's the set of all possible endpoints. Now, for a left endpoint Riemann sum, now I'm going to take from those and pick the left side of each one of these subintervals. So again, first subinterval goes from 0 to 1/2, 1/2 to 1, 1 to 3/2, and then 3/2 to 2. So essentially, all I'm doing here is I'm going through and picking out the left edge of each one of these. So when we do a left endpoint Riemann sum, you will use all of those numbers except for the very last, which is B. So that is my set of left endpoints, 0, 1/2, 1, and 3/2. Once I have those, again, these are x values. They determine where I'm going to touch the graph to actually create the rectangles. So once I have these, now we're going to go through and calculate our heights. So again, for the heights, notationally, the first height that I use, I'm going to go to my first endpoint, 0, and I would sketch the rectangle as tall as the curve is at x equals 0, which in this case is 4. So that would be my first rectangle. I would want to know that area. So that first height is the value of f of 0. The next height would be the height at the next x value, or the y value at the next x value. So at 1/2, that's where I would draw that rectangle. And then f of 1, and then f of 3/2. So we don't always have to list out these heights, but I just wanted to do it for this first one so you guys see what it is we need, okay? So that's how we would actually go through and build this if we wanted to do it the long way. We do each rectangle's area and then total them all up. But once I have this information, then we can just simply set up our formula. So the fastest way here, and again, this is always going to be an approximation until we learn how to find the real deal area. So that's why I do want to make sure we always use that approximation symbol. So our area under that curve or that region would be approximately equal to our common width. Again, each one of those rectangles has a width of 1/2. So that's going to be out in front. And then on the inside, it is the sum of all of these heights. So the first rectangle has a height of f of 0, then f of 1/2, f of 1, and then finally our last one would be f of 3/2. Now, setting up every one of these approximation problems is going to have some kind of line that looks like this. But then after that, that's where each problem will differ. It just depends on how the information is being presented. With a graph, there's no substitution that has to go on here. We just simply look at the graph. Sometimes we may have to estimate, but we're going to just use the height or the y value of the graph that's given to come up with these heights. So for this one, my area will be approximately equal to 1/2 times f of 0. That one we don't have to estimate. We know it's exactly 4. But then f of 1/2, let me erase these rectangles. Now, you guys have seen me draw them. Sometimes you may have to do your best to estimate y values. So right there, so if you carefully look at these tick marks, there's 2, there's 4, so this is 3. So that would be 3.5. So this is right about in the middle. So we're going to say roughly 3.75. Then at f of 1, so if I trace up, f of 1 looks like it's right at y equals 3. And then at 3/2, looks like we're right about here. So if I do the same kind of thing, that's 1, that's 1.5. So that looks like it's about 1.75. So from there, it's just adding and multiplying. So we're going to total all this up. So we would get 1/2 times 10.75, 11, so 12.5. Or we get 6.25 for the approximation of that area. Now, as far as units go, again, from geometry, you guys are probably trained that whenever you find area, we need some kind of unit squared. But when we do these problems on a coordinate grid, we don't really have units involved because we don't have a unit of measure for how long each tick mark is. Now, if you happen to be doing a problem where there is some kind of unit involved, then we would make sure that the units are being squared. But in this case, if you want to write anything, we can really just write units squared. All right, so now we're going to try to do the exact same thing, but now we're going to use right endpoint Riemann sums. So for this one, now I would go through to each of these endpoints, or excuse me, each of these subintervals, and we're going to choose the right side of each one. So that would be, the first interval would be at 1/2, then 1, 3/2, and then finally our b value of 2. So again, you can see how it kind of just shifts. So for left endpoints, we start with A and go up until the last one right before B. And then for right endpoints, we start at the second one and then go up until we get to B. So each one, there's one x value that doesn't end up being used, and it's always either A or B. So for this one, let me get rid of these old y points because we don't need we don't need all of them for this next one. So again, same process. Now I'm going to come up with a list of my right endpoints. Again, these are the x values. So in this case, it will be 1/2, 1, 3/2, and then my b value of 2. Then that would mean my heights would be f of 1/2, f of 1, f of 3/2, and then f of 2. And again, writing those out is not absolutely necessary. I just want to be very clear and make sure everyone understands the process. So then to set this guy up, our area will be approximately equal to, again, it's the same width as the left endpoint Riemann sum, but now inside we'll use some of the same endpoints. Any of these inner ones, any endpoint that is not, or any x value that's not A or B, would be used in both the left endpoint and the right point Riemann sums. The only ones that don't overlap or get used in both are the A and the B values. So we do already kind of know 3 of these numbers, but setting up the formula, it will look very similar to what we just did, except f of 0 is no longer in there, but now f of 2 is. Okay, so now if I replace, or actually let's write this down here. So f of 1/2, again, we already used those 3 values, so we already came up with estimates for those. So 3.75, 3, and 1.75. But then f of 2 would be 0 in this case. So we saw this example a little bit earlier ago, where sometimes a rectangle ends up being a 0 height, and that's because one of the endpoints is actually on the x-axis. So there's my first rectangle using the right endpoints, and then my second one, and then my third right there at 1.75. But then anytime that one of your endpoints has a y value of 0, then there basically is no rectangle there. It has a height of 0, so it's really just flat on the x-axis. So when that happens, you guys can see there's a lot of unused area here in that region. So this estimate's going to severely underestimate the real thing here. Okay, but let's go ahead and calculate this. So I end up with 1/2, and these guys total up to be 8.5. So then our right endpoint estimate would be 4.25, again, units squared, but you don't have to write that. I don't want you guys to think you always have to write that u squared. We typically will just get these values as just numbers and ignore the units for right now. So there you have it. You have 2 different methods for coming up with an approximation. Now, some people are going to try to argue that one method is more accurate than others, but if you really think about it, one's going to be over, one's going to be under. Our first one, our left endpoint, all of the rectangles stuck out over top of the curve, so we had a bunch of extra area that we didn't need. But now for the right endpoint, we have a bunch that are all of our rectangles are contained inside of the region, so we have a bunch of unused area or unaccounted for area. So this guy's going to be under it. So what we do know, though, is that the actual area has to be somewhere between these two. So we know for sure that the real area, it can't be more than 6.25 because that was an overestimate. and it can't be less than 4.25 because that was an underestimate. So we know the real thing has to be somewhere in between these two. And how we get to that correct answer, that is an important part of this process. That's actually a method called exhaustion that Archimedes used famously thousands of years ago to try and estimate the value of pi by taking an estimation or approximation and increasing the degree to which it is accurate. So that's kind of what we're going to be building up to here throughout these next couple of sections. Now, for both of those approximations, we do want to always consider whether it's an over or an under approximation. But there's actually some information about the function's graph that will dictate this. It's not always going to be, I have to graph it and look at it. We can actually use information from an equation to determine whether the approximation will end up being over or under. So if you think about some of the information about graph shapes that we've already talked about, the two main things that we've talked about is whether a function increases or decreases, and then whether a function is concave up or concave down. One of these things, is the controlling factor in making this decision. So let's do a little exploration here. So the graph that we just looked at on the entire interval, this guy could be described as a decreasing function that is concave down. So one of those two things is the reason why the left endpoint was the over and the right endpoint was the under. We have to kind of think about which one it is. So if we draw a decreasing concave down curve, it doesn't have to be at any specific point, but if I just make two arbitrary marks here, if I go to the left edge to make the rectangle, I'm going to stick out above, which means this is the over. And if I were to go to the right endpoint, I would stick or stay under the curve, so that makes this the under. So to decide whether it's increasing, decreasing, or concavity, all we have to do is just kind of pick one of those characteristics to change. For example, let's say that I keep this, I change this function to a curve that is still decreasing, but now I switch over to concave up. So if I had a concave up curve that was decreasing, then it would have to look something like this. Okay? So if that was my region, let's say that I'm going from that A to that B value, if I just pick 2 points in between these now, I switched from concave down to concave up, so this was the thing that I changed. Now if I go to left, I still am sticking out over top of the function. And if I go to the right, I'm still stuck under the curve. So changing the concavity did not change that result, which means concavity does not have anything to do with this. However, if I go back to being concave down and I go and switch it to an increasing function, so that would look something like this. If that's what my curve looks like from A to B, and I pick out 2 points, now when I go to the left edge, now I am under the curve. And if I go to the right edge, now I am over the curve. So changing the direction that the graph was moving is what changed the result here. So whether a function is an over or an under approximation actually has to do with the direction that the function is headed. When the function increases, like we just had, our left endpoint Riemann sum will produce an under approximation. Right endpoint will make the over. And when I switch it to decreasing, these flip-flop. So a left endpoint will be the over approximation, and the right endpoint will be the under. Now, is this worth spending time trying to commit to memory? Short answer is no. There's no point that you have to memorize this, but you should be able to recreate this and to remind yourself the way that this works. What would be worth memorizing is the fact that it's increasing, decreasing, and not concavity that controls this. But even if you forget that part, you can quickly sketch out the graphs that I just made here to recreate and kind of guide yourself through this same discussion. But this is an important piece to keep in mind. That way we can kind of guarantee which or between what two values our approximations are always going to be trapped between. So That is our first example. So let's try one more. What I would recommend, this is another graph one. So because we did one together, I would recommend you guys pause this and then try it on your own. And then when you're ready to check it, come back to me. Or if you don't feel like watching another example of graph because it really is the same kind of thing, then you can always skip ahead to the next kind of example. All right, but if you did try this one on your own, let's go ahead and walk through this. So my A to B interval is from 0 to 4. So to calculate delta x, I'm going to take 4 minus 0. I'm using 4 equal subintervals. So then my delta x in this case is 1. So then my list of all possible endpoints starting at A and adding delta x over and over again would be 0, 1, 2, 3, and 4. Now for left endpoints, that would be the set of all of those except for B. So 0, 1, 2, and 3. For my right endpoints, it would be everything except for A. So 1, 2, 3, and 4. Now, for the heights, again, it is just the set of the corresponding y values. So f of 0, f of 1, f of 2, f of 3. So then my area will be approximately equal to my common width, delta x, is 1, times f of 0 plus f of 1 plus f of 2 plus f of 3. So again, it's a graph, which means to get our important information, these y values, then we need to look at this graph. So again, 0, 1, 2, and 3 are the relevant points. So let's go ahead and plot these y coordinates, and then we'll go through and check their values. So again, always paying close attention to the scale of your graph so you guys are counting properly. So this would be 1, that would be 1.5, this would be at 3, this one's a little tougher, this is at 5's right there in the middle, so this would be at 5.5. So those would be our 4 heights. So 1 plus 1.5 plus 3, plus 5.5. So multiplying by 1 out in front is not going to change our answer, so it's essentially this total. So we would get 11 times 1 is 11. Now, even before we get to it, you can see this question is hiding down here. At the end, after we find both of these, I'm going to ask, is it an over or under approximation? So let's just go ahead and do this for ourselves as we're actually looking at it. So again, if you have the issue memorized, then you can just cite the case. But if not, when you're looking at the graph, just sketch it. If I just use the left endpoint, my left endpoint is sitting under the curve. So I know this is the lower end, which even before we get to the right endpoint, that's kind of a helpful thing to keep in mind. If I know that 11 is the under, if you go and do the other side and you get something smaller than 11, you definitely screwed up. This has to be something bigger than 11, or excuse me, greater than or equal to. There are some situations where our left and our right endpoints or our different sided approximations could actually equal one another. Those are special cases. So in this case, for this one, our heights would be, again, f of 1, f of 2, and so on until we get to our last b value. Then our area will be approximately 1 times the sum of f of 1 plus f of 2, and so on. So remember the first 3, we already know the heights for because we've already plotted those and looked at them from the left endpoint. But f of 1 would be 1.5 again, and then 3, and then 5.5. And then for f of 4, we will scroll back up here. So that puts us up here at 9. So then when I total all this up, we should get 19 for our overestimate. And again, I know that now because if I go to another set, doesn't have to be another set, but if I go to this subinterval, when I pick the right side to draw my rectangle, I will sit out above the curve. So this extra stuff pushes it to be an overestimate. So that's it. So I know for sure that the actual area has to be something in between 11 and 19. So again, what we're going to try to do with this process is keep pushing the, level of accuracy up and up and up. All right, so now let's take a look at another way of presenting our information. So the table below shows select values of a strictly increasing function f of x. So that would be helpful in determining what kind of approximation we're making, either over or under, for the interval of 1 to 13. So rather than giving you an equation or a graph where you can see all the different points for that interval, I'm just going to give you a select number of points. Now, if you notice on the chart, each one of these is separated by an equal amount. So when I ask you for these approximations, it's possible for me to ask for equal subintervals. But if these x values are not separated equally, I couldn't ask you guys to do that because you wouldn't have all the points needed to accomplish that task. So it really just depends on what kind of information you're given in the table that will determine what kind of subintervals we have. But in this case, we've got what we need. In this case, our delta x would be 2. But for this problem, any table problem, we don't have to worry about building a list of values of x because what they are is just what's on the table. Now, what you may want to do still is make a list of the left and right endpoints, because those will always be a subset of what's given. Or in this case, my left endpoints is, again, everything except for our b value. Now, this time I'm going to skip over writing out the heights, and let's just jump straight to our area formula. So the common width for each one of these would be 2, and then our heights would be f of 1, which is 2, and then f of 3, which is 3.1, and then f of 5, 3.8, and so on. So I'm going to have a rectangle of every single height except for our b value. Our f of b will not be used for a left endpoint Riemann sum. So again, with the table, there are some times where it can be difficult to kind of visualize what it is we're doing. So absolute worst case, if sketching out a graph and plotting these points helps you, then by all means do it. So 1, 3, 5, 7, 9, 11, 13. If you need to actually sketch out these points and just plot them so you have a rough idea of what's going on, then do it. There's no harm in that. So 1, 2, 3.1, 3.8. I don't even really need to label the y-axis. I just kind of want to see points plotted so that you can visualize what the curve may possibly look like. So you can connect them with straight lines. You can do all kinds of twists and turns that you want to. In this case, we do know that it's strictly increasing, so we do know that if we did connect it, it would be some kind of curve like this. Now, it may change concavity in there, but that part doesn't really matter as far as over or under. Again, it's just about it's increasing. So there's a rough picture of what it is that we're making. So with left endpoints, it would just look like this. Now, again, this isn't necessary. You don't have to always draw this, but some people are more visual learners, so seeing it sketched out is a big help to them, okay? So now we just do our calculations. So area would be approximately equal to 2 times the sum of all this stuff. I do like to do some mental math here, so that'll be 8.5. That will be 9, and then this is also 9. So we get 26.5, or when I double that, we get 53. So left endpoint on a strictly increasing function, I've already sketched out my rectangles. You guys can see there is extra space under here not accounted for. So this has to be my under approximation, which means when I go to do the right endpoint, I better get something bigger than 53. So for right endpoints, that list would be all values of x except for my a value. So that would be 3, 5, and so on, all the way up to 13. So when I write out my area formula now, it's still the same common width of 2. But now, again, if I were to sketch out my areas, or excuse me, my rectangles, let's ignore those little dots for right now. Right endpoint at 3, and then 5, and you guys can see, because it's an increasing function again, that right side is always going to be higher than the left, which is why that flat top of the rectangle is going to jut out above the curve. That's what's going to make this be an over approximation. So again, we're really just stealing the second, or everything that we listed up here except for that 2. So 3.1, 3.8, 4.7, whoops, 5.97, and then our missing y value of 12.1. Now, to speed up the mental math process a little bit, the only difference between this total and the previous one is I subtracted 2 from this, and then I'm going to add 12.1 to it. So that would be 24.5 plus 12 would be 36.6. Now, if I double that guy, I will get 73.2. And again, we got something bigger than our previous estimate, and that should make sense because this is supposed to be an overestimate. And once again, I now have a boundary of what I think what I know the actual area has to be equal to. The real area must be something between 53 and 73.2. All right, now, the last way that I can present information about the function is if I just give you the equation of the function. Again, this is definitely the most difficult, just because it takes more, sorry, I shouldn't say most difficult. None of these are overly difficult. None of these really require all that much work involved. And realistically, if you really think about it, we're not doing any calculus. There's nothing that I've shown you guys so far in this video that you would not have been able to do last year in pre-calc or even a couple years ago in Algebra 2. All we're doing is finding the area of rectangles, which is basic geometry. You learned how to do that in middle school. So up until this point, we have not done any calculus. So even when I say this is more difficult, it's not difficult. It's just more difficult to get to the y values. That's really the only difference here, is now we're going to have to plug numbers in to calculate what the y values are. Okay? So for this one, I want to find the area approximation for the function f of x equals negative x squared plus 2 on the interval from 0 to 1. So 0 to 1, that is my a and b value. That's my interval. So for delta x, for both of these, we're going to use 5 subintervals. So my delta x would be 1 minus 0 divided by 5, or 1/5. Or to make it simpler for us, I'm going to use 0.2 as my delta x. So for this one, because I don't have a table, I am going to list out the possible values of x. So again, starting at a, and then we're going to add our delta x value all the way up until I get to our b value. So those are my possible points that we are endpoints. So now for left endpoints, again, it's just going to be the set of everything except for b. So for this one, I'm going to jump right to setting up my area. So the common width of 0.2. And then this one, we definitely want to write out the height notation. Because again, for the table ones, it's kind of unnecessary because whatever this value is, we don't need to see the value of x going in because we're just reading it off the table. But for these, it is kind of important just to keep things straight, to know what value of x is going into the function for each round of this. So because we're going to have to do a whole bunch of substitution, then it is kind of helpful to see that notation written out. So now we just have to go through and evaluate all of these. So again, it's not that this is like super difficult, just more time consuming. That's really the only big down or drawback to working with the actual equation. But not all of them are going to be crazy difficult. So f of 0, 0 squared is 0 plus 2, so that would be 2. Then for these guys in the middle, you were just squaring those x values and then subtracting that from 2. So like if I write all these out, 0.2 squared is actually 0.04. 0.4 squared is 0.16. 0.6 squared is 0.36. And then 0.8 squared is 0.64. So basically, I'm just going to take each one of those, think about dollars and cents, and subtract it from 2. So $2 minus 4 cents, that would be 1.96. Minus 16 cents, 1.84. Minus 36, 1.64. And then minus 64 is 136. And then, oh, whoops. Actually, sorry. Added in an extra endpoint here. Even underlined them and everything. Sorry. Remember, for left endpoints, we would actually stop at 0.8. So that will actually be our last endpoint. So we don't need to do f of 1 yet. We'll save that for the right endpoints. So 1.36 is the last height. And that's an easy mistake to make, but do check yourself. If you want 5 subintervals, then we should only have 5 heights. So now we're ready to combine these guys together. So we will get 0.2 times our total here. So 1.96, these two will add to be 3.8. These two add to make 3. So my total here will be 8.8. So then to multiply this, if you're trying to do it mentally, multiplying by 0.2 is the same as 2/10. So it's like I can double this guy and then move the decimal point back 1 spot. That's what dividing by 10 does. So this would be 17.6, but then when I move the decimal point back, we'll end up with 1.76 for our final answer. Now, for sketching out our curves to trying to decide increasing or decreasing, remember that the function does have to be always increasing or decreasing. If it changes directions, then what we talked about earlier goes out the window. We can't decide over or under. There's no rule that always follows when it changes directions. But if we do have a strictly decreasing function like we do with negative x squared plus 2, if you guys remember, this is a concave down parabola, and it is shifted up 2 units. So I'm going to start at 2 when x is 0, and by the time I get to x equals 1, we are to a y value of 1. So my curve looks something like that. So then the region just goes straight down to the x-axis. So if I pick the left endpoint between two of them, because the curve's decreasing that whole time, we will have an overestimate here, okay? So now when I go to do my right endpoint, I should get something smaller than 1.76. So for right endpoints, if I set up my formula, my area will be approximately equal to same common width, but then multiplied by f of 0.2. So again, right endpoints, we skip the first guy, and then we start with the second one. So then I'll cycle through all these other ones, but now this time I will need to use that f of 1 that I tried to use a little too early last time. So now as far as heights go, that is one nice thing when you have to do left and right endpoints. You already calculated all the difficult y values. So that part's done for us, 1.96, 1.84, and we even know what those total up from because we wrote it down from before. But now f of 1, if I plug that into negative x squared plus 2, will give me negative 1 plus 2, or 1. So again, these make 3.8, these make 3, so this would be 0.2 times 7.8 this time. So if I double it, move the decimal point back 1 spot, we end up with 1.56 for our underestimate. So you can see for this one, these two are actually fairly close to one another. So if we used either of those for our approximation, we can't be very far off from the actual area. So again, as we refine this process, we're going to talk about how can I make these estimates even better as we build this process along. So from there, so now you guys have seen examples of the left endpoint or right endpoint Riemann sums, whether I give you a graph, whether I give you a functions equation, or if I give you a table of values. So just keep that in mind that it can happen all kinds of different ways. You just have to be prepared for all those different possibilities. Now we're going to take a look at something called the midpoint approximation. So the first set of problems, we talked about how to use the left or right endpoint, but we've seen how one side's going to be over, one side's going to be under. So if you know that going into it, and we want to make this process as accurate as possible, why not come up with a better way to make our approximations even more accurate? So one method to do that is using the midpoint. If we know one side's going to be above and one side's going to be below, then if you kind of think of it like the 3 little bears, right in the middle is going to be the sweet spot. So in between the left and right endpoint, or the midpoint of each subinterval, should yield a even more accurate result than the left or the right. Now, a common misconception is that midpoint approximations are always going to be the exact thing. A lot of people think that the exact area is always right in the middle of our over and our under approximations. That could possibly be the case, but it's not always the case. Really, the only time that would happen is if I was using a linear function to, or that was the function I was using to approximate the area for. So typically what's going to happen is it's somewhere in the middle, but it's not right in the exact center of the two. Otherwise, this would be a really easy problem and we wouldn't need calculus in the first place. So not much is going to change about the process, though. The only difference is how we go about finding our x values that we then substitute into the function to get our heights or the y values. So if we, this is actually the same function that we used for the last problem, same interval, but now I want to use midpoints instead of left or rights. And we are also going to change it to use 4 equal subintervals rather than 5. So that part's a little bit different, but again, that doesn't change the overall process. So first thing we need to do, same as always, we're going to come up with our delta x. So 1 minus 0 divided by 4 gives me 1/4. You can use a decimal, but because we're going to be doing midpoints, I recommend that you guys keep it to fractions for the time being, okay? So for this, that's my delta x. So now let's build a list of all our x sub I. So that would start at 0, and then 1/4, 2/4 is 1/2, 3/4, and then 1. Or if you think about it on a number line, we're going to go from 0 to 1/4 to 1/2 to 3/4, and then to 1. So what we're going to do essentially, instead of picking the left or right for each one of these subintervals, we're just going to go right in the center of each of these guys. Now, how you find the middle is kind of up to you. There's lots of different strategies to do this. The simplest is add the left and the right endpoint and then divide it by 2. That will always get you to the exact center of any two numbers. It doesn't matter if it's a calculus problem or not. So for example, 0 plus 1/4 is 1/4. Divide that by 2 gives me 1/8. That is my first midpoint. That is the first x value that I will use to generate the height of our rectangle. Halfway between 1/4 and 1/2. 1/4 plus 1/2 is 3/4. Half of 3/4 is 3/8. So that is my next midpoint. So what you notice here, though, is that the distance between one midpoint to the next, it's still the same thing as my delta x. Whoops, not 1/2, 1/4. So that will always be true. When you go through to find these, that's why I said there's a bunch of different strategies that you can use for these. It's really about what you're most comfortable with or what's simplest for you. So if I know that, I'm just going to keep adding a 4th or adding 2/8 in this case. So that'll take me to 5/8 and then 7/8. So those are my 4 midpoints. Those are the values of x that I'm going to use to substitute into the function to generate the height. Now, setting up the area formula, though, is exactly the same process. It's just we're working with different numbers now. Now my delta x is 1/4, and then my heights would be f of my first endpoint, or excuse me, midpoint, f of 1/8, then f of 3/8, and so on. So the setup, it's really the same thing. It's just you're using midpoints as your x values instead of left or right endpoints. So from there, we're going to substitute these values of x in. A little bit more difficult now just because of the fractions involved. And again, you could do it with decimals, but I think squaring fractions is easier than squaring decimals. Now, one thing to keep in mind, when I square all of these fractions, the bottom will be out of 64. So I'm going to go ahead and rewrite this guy as negative x squared plus, instead of 2, I'm going to rewrite this as 16/8. Okay, that way they already have the same denominator, and it makes it a little bit, or excuse me, not 16/8. We got to do it in 64ths. So 64 times 2 is 128. So 128 64ths. That way I already have everything matched up, ready to go. All right, so now this would be 1/4 times 1/8 squared is 1/64 minus, or subtract that from 128. So I'd have 127 64ths plus 3/8 squared is 9. So negative 9 over 64. That would leave me with 119 64ths. 5 squared is 25. So that would leave me with 103 over 64. and then 7 squared is 49, so that would leave me with 79 over 64. So then from there, we're just going to combine all of those fractions together. So 127 plus 119 plus 103 plus 79 gives me 400 and make sure I added all those up right. Yep, 428 over 64. And now multiplying by 1/4. This numerator is actually divisible by 4, so I'm going to reduce this to make it a little bit easier. So we get 107 over 64, or let's get a decimal for that. That comes out to be roughly, it does look like it would, yeah, it doesn't reduce. So we get we'll go 3 decimal places, 1.672. So that is, so again, when it's a midpoint approximation, we can't really qualify it as over or under, because we'd actually have to see the curve and how all the rectangles relate to the curve itself to know whether there's more extra area or more uncovered area underneath the curve. But what we do know is that this midpoint approximation is better or closer to the actual thing than either of our previous approximations. So 1.672, you guys can see that that is somewhere in the middle of this over and under approximation. So that kind of confirms what we were talking about earlier. So that's how we can approach midpoint problems if I give you the function. If I give you a table, so this is actually going to go back to one we looked at earlier when given a table. But if you notice here, midpoints, or excuse me, when we did just left or right endpoints before, we did 6 equal subintervals, but now I'm only using 3. And that's because when you do midpoints with a table, you're kind of limited to what values of x you can use. If I tried to do 6 subintervals again, my subinterval would be from 1 to 3. Well, the midpoint of that is 2, and you don't know what the y value is when x equals 2. And without the equation or a graph, there's no way to come up with a value for that. So that's why a lot of times when you are doing these midpoint problems given a table, you'll have more values of x than what it might look like you need. But that's because with 3 equal subintervals, my delta x would be 13 minus 1 divided by 3, or we get 4. So the first subinterval goes from 1 to 5. So they're actually kind of giving you the midpoint that is needed to do these as part of all the information on the table. So from 5 to 9, 7 would be the midpoint, and then 9 to 13, 11 would be the midpoint. So we can still do these with table problems. So our delta x is 4. So then our 3 midpoints would be f of 3, f of 7, and then f of 11. Or again, we're just taking the y value straight off the chart. So 3.1 plus 4.7 plus 7, we would get 4 times 14.8, or 99.2. And that's it. So again, with the table, it is still possible that really the only difference is you're going to have some extra points, but that's because your midpoints are actually kind of hiding in the middle of those other guys. So that's the midpoint. Not much to it. Again, it's very similar to the left and right endpoints, just a different way of going about the values of x will be used to build the rectangles. So the last one, I know this is another marathon, but lots of different ways to talk about estimating these areas. So for the last way, we look at what is definitely the most accurate of all these methods, but it's also the most difficult. It's a more difficult formula because it's a more difficult shape to work with. So that is the trapezoidal rule. So all the other methods, the first 3, all relate or are all based on using rectangles to come up with the estimates for the area. But the problem is when you use a rectangle, you're using flat-topped shapes to represent curves that twist and turn or increasing or decreasing. Well, if you know that a curve is increasing or decreasing, a constant function is never going to do a good job of estimating what that curve is doing. So instead of using flat-topped rectangles, we use another shape that has a slanted side to it, but is also still relatively easy to calculate the area for it, and that is a trapezoid. So most people, when you hear trapezoid, you think of something that looks like this, like the Pizza Hut logo. But that's just one kind of trapezoid. Another kind of trapezoid is what's referred to as a right trapezoid. So remember, a trapezoid in general, the definition is a quadrilateral with only one set of parallel lines. So top and bottom, which we refer to as the bases of the trapezoid. But I can make a trapezoid that's kind of like this guy chopped in half, where there are two right angles here. So one side is vertical and the other is slanted, but the top and bottom, the bases, are parallel. Well, this is typically how trapezoids are oriented, where the bases are on top and bottom. But again, they're just shapes. You can turn shapes any way that you want to. So for us, and what we want to do, we want the parallel sides running up and down. That way they can correspond to values of x on our number line. So this would be an x value. This would be an x value. So if the parallel sides run vertically, then our right angles actually are going to sit on the x-axis, which allows the slanted side to be up where the curve is. And why that is so beneficial to us is now, instead of using a constant function to represent a curve that's changing, now we can use a linear function to estimate the curves of that given function's graph. And we've already done that in the past in calculus, where we use a secant line to try and approximate the rate of change of curves over intervals. That's essentially what we're doing now, but we're using it to our benefit to come up with these more accurate estimations for area under a curve. So the way this works, just to do a little bit of review, again, it's the same process as what we did before as far as taking the whole interval and breaking it up into chunks. So we still have subintervals, which is dependent upon how big the whole interval is and then how many subintervals we have. But now we want to find the area of trapezoids made with those different endpoints. So just to review, the area of one trapezoid. So I'm going to draw it the way that we'll see it here. So this is my base 1, this is my base 2, and this is actually going to be my height. But if we have all of that, then the area formula for a trapezoid is 1/2 times the sum of the bases multiplied by the height. So that's the formula from geometry, nothing super crazy there. Again, there's a proof for this. Essentially, it's a trapezoid can be thought of as a parallelogram that we chop in half, so it's kind of the average of the two bases. That is what is technically the base dimension for that parallelogram. So it's a little confusing, but it's not too complicated. But that is our formula that we use for the area of just one trapezoid. But if I have n trapezoids, so if I keep adding all of these up over and over again, that would just be the first two bases used multiplied by its height, but then the next set of bases would be used. So in this case, actually, let's rewrite this. So if I were to use the way that this is set up right now, the first set of bases on this diagram would actually be x sub 0 and x sub 1. Okay, now for the second trapezoid, the first base used is x sub 1. See how this is the first for the second guy, and then x sub 2 times its height. Actually, let's label this as, actually we can leave that. So again, the height in this case is actually this x dimension, okay? And then we'll do it again for the third one and so on, but then at the very end, in this case, we would have 1/2 times x sub 3 plus x sub 4 times that same height. So we really could just repeat that process over and over again. But if you notice here, a couple of things are in common in each one of these sets. So each one has a 1/2 out in front, which, remember, just like with the rectangle rule, when there's something in common, we can pull that out in front to speed up the evaluation. I don't need to multiply all these by 1/2 individually, just do it at the end. They also all have an h value, and that's because that h is like that common width of our rectangles. When we turn it on its side, what used to be called the height is really the width of each one of those. So we could pull that h out, but instead of calling it h, let's call it what it really is, and that would be our delta x. Now what's left inside is, oh, and you know what? I'm sorry. not x sub 0. These should be f of x sub 0. I apologize. Remember that we're using those x values to calculate the heights. So the heights would be f of x sub 0, f of x sub 1, and so on. I apologize. That was a big goof. So all these guys should be f's. Okay? But when we pull all that common stuff out, what's really left here is I have f of x sub 0, and then I have f of x sub 1 there, and I also have it here. So a simpler way to write it is 2 times f of x sub 1, because that height got used twice in all of the math going on between all of those. X sub 2 would have been used twice. It would be used for the second trapezoid and for the third one. So I would have 2 of those as well. So 2 times f of x sub 2. X sub 3, same thing. It belongs to 2 trapezoids. But then at the very end, f of x sub 4, that very last one, it was only used one time, just like the very first one. So if you really think about it, every time, no matter how many subintervals or trapezoids that I have to set up here, all of these middle x values will be used twice to determine the height of 2 different bases. It'll be the second base in the first one, and then the first base in the next trapezoid. So we can speed this formula up by remembering that all of the inner heights have to be doubled. Our f of a and our f of b values, those are only going to be used once because they're only used at the very beginning and the very end. But all the inner ones are always going to get multiplied by 2 because they're always going to be used more than once. So what we end up with is a very similar formula to what we've seen in other problems with the rectangle stuff. This is the shortcut problem or shortcut formula when we have equal subintervals for our trapezoidal rule. So let's try one. Okay, it's going to feel like a very similar process because we're really doing the exact same stuff that we did before. So we're going to use the trapezoidal rule now to approximate the area under the curve of sine of x from 0 to pi for n equals 4. So it's going to start off the same way. I'm going to have delta x, so pi minus 0 divided by 4, or pi over 4. Then if I want to list out my endpoints, that set would go from 0 to pi over 4. 2 pi over 4 is really pi over 2. 3 pi over 4, and then pi, or 4 pi over 4. So the only big difference now is when I go to set up my formula, each height doesn't get used once. Again, all of these inner ones will get used twice. So what I like to do as a reminder, and this is kind of why I really like listing this stuff out, I am going to box these middle guys. That's kind of my brain trigger to remember those numbers have to get doubled, okay? We use these twice. So because they use twice, we have to do something different in the formula for them. So now, for area of the trapezoidal rule, it is approximately equal to my delta x divided by 2. So in this case, pi over 4 divided by 2. Remember, if I take a fraction and cut it in half, it's really like we're just multiplying the denominator by 2. So half of 1/4 would be 1/8. So we got pi over 8 out in front. And then inside, I am going to set this up with all the notation. So f of 0 goes first. It's only used once. All the middle guys got to get doubled. So 2 times f of pi over 4, because it's used twice. 2 times f of pi over 2. 3 pi over 4. But then the last guy only gets used once. So there's my setup. Now it's just a matter of going through and evaluating all of these. So pi over 8 times f of 0. Now we have a graph here that will help us. But remember, this is really just evaluating trig. So our function is sine of x. Y coordinate at an angle of 0 is 0. Pi over 4. Now I do recommend writing out 2 times the answer just so you guys don't get tripped up. Pi over 4, my y coordinate there is root 2 over 2. Pi over 2, up top, my y coordinate is 1. 3 pi over 4, also square root of 2 over 2. And then back down at pi, y-coordinate there is 0. So don't need to worry about the last guys. But now when I double all of this stuff, these 2's here are going to cancel, and then this just turns into 2. So on the inside, we end up with my whole number 2 plus square root of 2 plus square root of 2 is really 2 square roots of 2. Now this isn't a nice way to write all of this. One way, if I wanted to write all of this in simplified form, I could write it as, if I distribute the pi, I could get 2 pi plus 2 pi square root of 2 over 8. But then everything there is divisible by 2, so we get pi plus pi over, or times square root of 2 over 4. But that's not all that nice of a way to write that answer. You guys aren't going to know what the value of that is anyways. So let's get a decimal for that value. So pi plus pi times the square root of 2, all divided by 4, gives me roughly an area of 1.896. Yikes. Don't know what happened there. 1.896. That's it. Now, when we do the trapezoidal rule, the way that we can present the information, that's always going to be the same thing as the rectangle. So whether I ask you for left endpoint, right endpoint, midpoint, or trapezoidal rule, I could give you the equation of the function. If that's the case, you find your values of x for your subintervals, pick the ones you need, plug them into the equation to get the heights, or for trapezoids, the bases, but they're still really the 2 heights. If it's a graph, then we simply look at the graph, figure out the heights based on the actual curve that's given. But if I give you a table, it's still the same way as when we did the rectangles. Really the only difference is we're going to use the middle chunk twice again. So just like I did on the previous one, as soon as I realize it's trapezoidal rule, again, instead of me just giving you what you need to find the x's and then have to do more work to find the y's, you have them both. So I'm just going to make my little note here that I want to use this. It's supposed to say twice. Yeesh, I don't know what happened. Apparently my tablet is tired as well. So we're going to use all of these values twice when we set up the formula. It looks even worse, but we're going to leave it. So area is approximately equal to. So my delta x for this case, if you look at it, it looks like all of these are evenly spaced. So most of the time it's safe to assume, but it's still a good idea to go ahead and calculate delta just to be safe. 19 minus 4 divided by 5 is 3, and that is the width here that is given to us. So some of you may be wondering, well, if it's 5 equal subintervals, why do we have 6 numbers? Well, remember, one subinterval is from the first guy to the second, second to the third, third to the fourth, and so on. So if it is 5 equal subintervals, you need to have 6 set of points. Again, that's the idea, just like with all these other ones, when we make our list of x values, there's always going to be one more than the number of subintervals that we end up using. So for this one, again, it's delta x divided by 2 because of the 1/2 that's in that trapezoid formula. So we get 3 halves out in front, and now it is f of 4 plus 2 times f of 7 plus 2 times f of 10, and so on. Now, I'm not going to write all of these out because it's going to take longer than what it's needed. But again, the only one that is not doubled will be the last guy, anything that's not in that box. That's why I recommend you guys putting that box around there so you don't forget. So again, this step is really just if you need that to help remind yourself of what math we're doing. But if you feel confident, then we could really jump straight to these values from the table. So my first height would be 21 plus 2 times 14 is used as a height twice. So is 11, so is, 9, and then so is 8. And then the last height of 4 is only used one time. So now it's just a matter of going through and doing all this math. So we got 21, 28, 22, 18, 16, and 4. These guys give me 20. These guys give me 40. I don't know what is going on. And those give me 49. So we have 3 halves times 109, or half of 327 gives me 163.5. And that is our trapezoidal rule approximation for the area under that curve. So again, it's very similar to the table problems with rectangles. Again, the only difference is that change in formula. Now, what happens if I have unequal subintervals? Well, the only thing that changes is I can't use the shortcut formula anymore. So again, the whole idea of these equal subintervals, that's what allow us to use these sped up formulas. Having the common width pulled out in front, having the 1/2 pulled out in front, having all these twice used heights already multiplied by 2. All of that can be done all at once when we have equal subintervals. So if you have the choice, always choose to use equal subintervals because it makes everything easier to do. But there will be certain situations where we don't have that choice because the information given to us doesn't allow for that to happen. So if that's the case, yes, it's a pain in the butt to do, but all you really have to do is just find the area of a trapezoid 6 times, or however many subintervals they ask for. So it's not difficult, it's just time consuming. So I do want to show you one just so that you guys are all aware of how to do this if you come across one like this. So again, they're straight up telling us that these are unequal subintervals, but you'd also be able to tell that just by looking at the intervals. 1 apart, 3 apart, 4 apart, 5 apart, 6 apart, 7 apart. So they're actually getting wider as we go. And there are certain curves where that may actually be beneficial or more accurate to do that. And there's no rule, because this is just an approximation, that says we can't do that. But because this is a table, we have no choice. We have to do what the points that they give us tell us to do. So basically, I'm just going to go through and do the area 6 times. So for the first one, I'm going to take 1/2 times the sum of these 2 heights. So 1.2 plus 2. Hopefully my tablet doesn't have a mental breakdown while I'm writing this. And then we're going to multiply it by the width of that interval. So from 1 to 2, that width is just 1. So if I do all that math, I get 1/2 times 3.2 times 1. I don't need to write again. So we get 1.6. That is our first height, or excuse me, first area. That's the area of the first trapezoid. So you're just going to go through and do that for each of the 6 subintervals. So the second one, 1/2 times, I'm going to speed it up a little bit. The sum of these 2 heights is 6.1, and the width of that is 3. So I'm going to take half of 18.3, or, my tablet allows it, 9.15. Super annoying. All right, and trapezoid number 3. So for the third one, we will have 1/2 times the sum of these bases. That would be 10.1. And then times that one is 4 units wide. So this one, half of 4 is 2. 2 times 10.1 would give me 20.2. Or it doesn't matter what order we multiply in, whichever one is easiest. Okay, then for the fourth subinterval, we would have 1/2 times, yikes, 1/2 times the sum of those bases. So we're going from 9 to 14. So that would be 1/2 times 6 plus 6.3, or 12.3. And that one is 5 units wide. So I'm going to have half of 61.5, or 30.75. And then for our fifth trapezoid, this guy will go from 14 to 20. So we got 1/2. Man, it really does not like me writing 1/2, apparently. Must be a big decimal fan. So we got 1/2 times 6.3 plus 8, so 14.3. And then that interval is 6 units wide. So half of 6 is 3, times 14.3 would be 42.9. And then for our last one, just do it down here. Final one is, hey, you got a 1/2. From 20 to 27, so that would be 18.2 for the total of the bases or the heights. And then we are 7 units wide. So I'm going to have half of, and of course, let's see, that is 0.4127. So half of 127.4 is 63.7. So now your final job is just totaling up all of those areas. Again, I didn't do anything there that was super difficult. It was just time consuming. Doing all of those calculations is a little mind numbing and takes forever, but nothing there was above a 5th grade math level. We're just multiplying stuff together. So when we add up all of our areas, 1.6, 9.15, 20.2, 37.55, 42.9, and 63.7, we get a total area of, and again, this is still an approximation, 168.3. So again, just because we made the intervals unequal, it doesn't change the fact that we can do it or not. It just changes how we go about doing it. So, and realistically, even with equal subintervals, if anyone ever wanted to do it this way, find each one individually and add them all up. If that makes more sense to you, then by all means do it. But the more efficient way, when we have those equal subintervals, is to use that quick, easy formula to help speed up that process.